Okay, so for some reason my other video, there was no, I don't know, you couldn't see my pen, so we'll try this again. All right. Okay, so let's look at, this is what page bottom of page 85 and then 86. And we're trying to match the graphs to the descriptions in problem number 4 here on the page 85. So there's some descriptions there, and then also it goes to the top of page 86, and we're trying to match those. So I believe in the other video, I kind of looked at A. You save some money, and then you don't get any interest, and then you just leave it there. So that to me looks like this graph. So you're adding money over time, right? More money, and then that money just stays constant because you're not adding any more money and you're not getting any interest. So to me, this goes with A, all right? And it says what's your independent variable and what's your dependent. So you're putting money every month. So like these little tick marks would be months. So X would be in months. And then the Y would be what? The money that you have or the balance in that account would be your Y. Okay, so your independent variable is how many months, and then on the Y would be your money or your balance. All right, so that goes with A. All right, so let's look at B. Average monthly temperature in a given location. All right, so because we live in Iowa, if we lived in San Diego, maybe this wouldn't be the case. But because I live in Iowa, I am kind of thinking that this graph fits that requirement for B. All right, because, you know, you have this cold temperature, it gets warmer, gets super hot, then you have kind of the middle, and then it gets cold again, and so over time. Right. If you live somewhere where there's constant temperature, like San Diego, it'd be just kind of a straight line going across like that. So this would go with B. All right. And let's see again, time is almost always your independent. So here's the months, right? And then on the Y would be, the output would be the temperature. Seems to go with that one. All right, let's look at C. Population of bacteria doubles every hour. All right, so that would be exponential because it starts out small. So like you might start out with 1, and then you double and get 2, and then you double and get 4, and double and get 8, and get 16, and 32, and 64. So it gets big fast, but it starts out really slow. And so to me, that looks like this one right here. It doubles, so, you know, I start and it starts out slow, but then eventually over time it's going to just go up exponentially. So my independent variable is time, which is in hours. Right? And then what I'm measuring is either the population or the amount of bacteria or something like that. So that one goes, and that would be what? C, I guess. So this one is, oopsie, sorry. This is C. All right, let's keep going. Let's look at D. All right, so D is the height of a ball each second after it's shot from a catapult. Okay, so that to me kind of looks like this one. Because you start out at 0 or ground level, and then at some point after a certain amount of time, it's going to peak, and then it's going to slowly over time fall back to ground. All right, and so again, time, this would be seconds, is your independent variable, and then height of how tall the ball gets is your Y. So again, that one looks like D. All right, E, the number of days needed to build a bridge. All right, so if I erase this one. All right, so if I have 1 worker, how many days is it going to take to build a bridge? If I have 2 workers, all right. If I have 3 workers, if I have 4. So if I have 1 worker, it looks like it's going to take infinity to build a bridge, or 2 workers, or, you know, if I have little tiny hash marks in here, right? Now, if I have maybe 50 workers, you know, if this is 50, maybe that takes a certain amount of time to build. If I have 100 workers, maybe it takes this time. And then it kind of levels off, because to be honest, if I have 1,000 workers, you know, it really, a lot of them are going to be standing around doing nothing. So this kind of looks like the bridge building one. So this goes with E, right? And my independent variable is number of workers. So again, at some point, it doesn't matter how many workers you are, it's still going to take a certain amount of time because they're just going to be standing around doing nothing. And this time, the time is actually your y. And that's not normal. Usually it's your x. But again, the variable I have control over, my independent variable, is how many workers I have. And then the result of that is the time. So that's why that's the dependent variable. All right, so what's left here? What one haven't we done? I think we haven't done II. So let's look at that one. All right, so for that one, what's left? It looks like probably getting contagious virus. All right, so that goes with F. That's this guy right here. And what happens is, and here we have time, right, over here. So this would be what, days? And then this is the number of students is here. So again, an independent, dependent. But at first, it almost looks like it's exponential, kind of like this graph over here. Because at first, nobody's infected. Excuse me, they infect a few people, and then it kind of grows. But then it comes a point where it kind of levels off because people are getting healthy, and then kind of like there's no more people to infect. Right? So then as days go on, it just kind of levels out a little bit. People have all the people that are going to be infected are infected. Other people have immunity. And then eventually over time, you'll see that go back down to nobody having the virus. So this would be F. All right. Hopefully that helps with the issue. I apologize for that, but you couldn't see my markups the first time around.